Well, hello there. I hope you're doing well. In this video, we're going to be talking about Chapter 1.5, Energy Conservation in Collision. So up until now, I have mentioned that we could use energy calculations to calculate our collision, at least in elastic collisions, but we haven't done anything, done any of that. That's going to change today. Unfortunately, I don't have my writing tablet, so we're just going to have to stick with moving the shade around. Hopefully it will be helpful. If you have any questions, of course, do reach out to me, or when I see you next, I will do my best to answer them. Momentum is conserved in all collisions. A collision may be defined as elastic or inelastic. Elastic collisions happen when both objects continue to move. Inelastic collisions happen when they don't. More specifically, though, and that's the definition we've used up until now. But actually, an elastic collision is better defined as a collision in which kinetic energy is conserved. If the total kinetic energy before the collision is equal to the total kinetic energy after the collision is perfectly elastic. And in reality, only subatomic collisions come close to being perfectly elastic. The way we do that is by using this terminology. So that is the Greek capital letter, sigma. So sigma, EK before, and sigma represents the sum. So the sum of all kinetic energies before the collision. So in this case, we usually use two objects. So the sum of their kinetic energy before is equal to their sum of their kinetic energy after. And in case you have forgotten, kinetic energy can be found using the formula 1/2 mv squared. So the sum, the delta E k, would be 1/2 mv squared for the first object plus 1/2 mv squared of the second object. In this case, for example, we have one ball moving, one ball stationary. So this would have kinetic energy. The stationary one would have no kinetic energy. And upon their collision, now the first object has no kinetic energy, and the second object has kinetic energy. If this were an elastic collision, then all of the energy from object 1 would be imparted to object 2. If it were inelastic, then some of that energy would have been lost. And yeah, I think that's it for this. Yeah, that's it for this one. So the next slide. Inelastic collisions occur when kinetic energy is not conserved. So the kinetic energy before, or the sum, of the kinetic energy before is greater than the sum after. Up until now, or no, we haven't actually done any, so never mind. Yeah, so the sum before is greater than the sum after. Breaking, bending, crumpling, or locking together is going to be evidence of an inelastic collision. And this very, very hard to see picture is a van that's crashed into a wall. So this is a photocopy of a photocopy of a photocopy of a photocopy. Who knows how many times it's been copied, but there we are. So, and we can tell how much has been lost. So the sum of the kinetic energy lost is equal to the amount of kinetic energy before minus the amount after. Right? It's the difference between the two amounts. Sometimes kinetic energy is also expressed as a percent loss. And the way we do it, as I'm sure you can imagine, is the kinetic energy lost over the initial kinetic energy. So we first of all find the kinetic energy lost by subtracting the difference, or by finding the difference. Then we take that lost, divide it by our initial, multiply it by 100% to get a percentage of the original kinetic energy that has disappeared into other energies. Not disappeared, transformed into other energies. And that's basically it. That is the learning. So let's do an example now of this by doing the so-called quiz. Not a quiz, not for you at least. A ball with a mass of 1 kilogram is rolling on a frictionless surface with a speed of 5 meters per second, 5.0 meters per second. Got to remember my sig digs. It collides with a stationary ball B of 16 kilograms. After the collision, ball A deflects 35 degrees below the horizontal, what we would generally call 35 degrees south of east, with a speed of 4.0 meters per second, as shown below. We have ball A, 10 kilograms going 5 meters per second, collides with ball B, and the momentum, you just multiply them together, is 50 kilogram meters per second, or 50 Newton seconds. Collides with ball B, and ball B, maybe I can zoom in and get a better look. Let's see here, because I want you to be able to see a little better what's going on. There we go. So ball A is deflected 35 degrees, and it is moving with a speed of 4.0 meters per second, which gives a momentum of 40 kilogram meters per second. It's a little hard to see there, which means the remainder of the momentum, if it's an elastic collision, will be imparted to, the momentum is always conserved, so the remainder of the momentum is going to be imparted to our object B. Object B, we only know its mass is 16 kilograms, so we need to find out its momentum and then its velocity. And so this is how you want to set up your equation. And feel free to pause it if you want to get a better look at things. With that now, it's time to do the math. And this is familiar math. This is what we've been doing for the last week or so. First of all, it says complete the diagram above. Already completed it for you. So make sure you filled that in. Drawing the vector representing the final direction of ball B. And then the second part, the more important part for our purposes, is calculate the velocity of ball B after the collision, show all the work, include the direction, and the units. It is velocity, of course. Therefore, the first thing we need to do is find the amount of momentum in the x direction, and then use that to find the momentum in the, after the collision in the x direction. So before in the x direction and after in the x direction. To find the momentum of ball A, we know that we had 50 Newton seconds of momentum in the beginning because all of our momentum was in the x direction. After the collision, ball A has a momentum of cosine 35 times 40. Because that's the trigonometric ratio that we use, plus the unknown momentum of ball B in the x direction. Cosine 35 times 40 is equal to approximately 32.8, 32.766. Remember, it's probably a good idea to keep those units. So 50 is equal to 32.766 plus the remainder momentum from ball B, which, when we solve for it, finds that the momentum in the x direction after collision of ball B is equal to 17.2339 kilogram meters per second. With the x direction figured out, now it's time to work on the y direction. Initially, we had absolutely no momentum in the y direction. So from that, we know immediately that the momentum for ball A in the y direction is going to be equal to the momentum of ball B, equal in magnitude but opposite in direction. To find out the momentum of ball A, since it's going down, the negative there is added just to make sure it's the right sign. The momentum of ball A in the y direction is the sine of 35 multiplied by 40, which is our ratio, once again, trigonometric ratio, plus the momentum of ball B, or after you calculate that becomes 22.943. So the ball A has a momentum of 22.943 Newton seconds, or kilogram meters per second, in the downward direction, which means ball B has the same magnitude but in the up direction. We have our two values then for ball B. So what we could do is put that right there. The momentum for ball B in the x direction is 17.2339, and in the y direction, 22.943. The next step, of course, is using good old Pythagorean theorem to calculate what the momentum, the magnitude of the momentum is in the actual trajectory. So the square root of a squared plus b squared, square root of 17.2339 squared plus 22.943 squared gives us a magnitude of 28.6947 kilogram meters per second. So that number would go right there, 28.6947. Finally, we need a, actually, you know what? We don't need a direction for this one because it's not asked. We only care about the velocity. Normally, you would need a direction. But since, or wait, maybe it actually asks. Let me double check what it asked for. Yeah, and we need a direction. We will have to find the direction after. Sorry. But we can do that for now. We're going to go to the velocity first, I guess, because that's what my key has. So to find the velocity, or the speed more accurately, because we don't have a direction yet, of ball B, we take that momentum that we just found and divide it by the mass of ball B. The momentum was 28.6947, and the mass is 16. So the speed is 1.79 meters per second. Rounded to proper significant digits, 1.8. Finally, we need a direction. So now we'll use our trigonometric ratio. And as I've mentioned before, the best practice is to use the tan ratio because the hypotenuse comes from a calculation of the opposite and adjacent sides. So in order to avoid causing additional errors, that's what we should generally do. So the momentum in the y direction was 22.943. Momentum in the x direction was 17.233. 9? Oh. Yes, 2339, which gives us a ratio, or pardon me, a direction of 53 degrees north of east. So we have 1.8 meters per second, 53 degrees north of east. The last thing, though, is to figure out whether this is an unelastic collision or an inelastic collision. Up until now, it's been very obvious. We've had them stick together or not. Now, it might be, it might not be. We'll have to find the answer using the conservation of kinetic energy. Once again, if the kinetic energy is conserved at the beginning and the end, then it is elastic. If there is a loss of kinetic energy in the system, it is inelastic. So we compare our kinetic energy before with our kinetic energy after. Since ball B is not moving in the beginning, its kinetic energy is 0 and is completely dropped from this equation. Therefore, the kinetic energy of ball A initially, 1/2 mv squared, must be equal to 1/2 mv squared of ball A after the collision plus 1/2 mv squared of ball B after the collision if this is an elastic collision. And the fact that there is a greater sign kind of indicates that they probably are not conserved. But we'll double check. So, first of all, 1/2, the mass of ball A is 10 kilograms. The velocity is 5 meters per second. So 1/2, 10, 5 squared. Then after the collision, it becomes 4 squared. And the other one is 16 kilograms and a velocity of 1.79 squared. You throw that all into your calculator, you'll find that initially there were 125 joules of energy. And then we have 80 plus 25.63. And just looking at that now, you can see it's not going to be equal. We had 125 joules of energy, but 125 joules is greater than the total energy after collision, 106 joules. Therefore, the collision is inelastic. And that's it. Therefore, the key, or so, in recap, in summary, the key to determining whether a collision is elastic or inelastic, based on energy, is by calculating the amount of energy before the collision, the sum of the total energy, I guess we should say, and the sum of the energy after the collision. If they are equal, it is an elastic collision, and if the initial energy is greater than the final kinetic energy, then it is an inelastic collision. And that's it. If you have any questions, please do let me know. I hope you have a fantastic day, and I will talk to you later.